Some people have probably got a calculator that just does that. And that's an acceptable solution. Who's figured out a few binary digits? All right, I'll move on. It could be an interesting exercise. They're saying this stuff's not an exam, but it could be an interesting exercise. Okay, so there's a number, and in binary, I think it's 1.110101 to the base 2. It looks a bit weird, but you can write fractional numbers in binary just as you can write decimal numbers in binary. And how did I get that? I did it two ways. One, I used a calculator. The other one is I did it in MATLAB. I just start with a number at the top, and then where it had a 1, right, I subtracted 1, so it was a number then less than 1, and then I multiplied it by 2. And if it then is greater than 1, so you see what I've done there. I multiply it by 2. If it's greater than 1, I subtract the 1 and call that a binary digit 1. If I multiply it by 2 and the result is less than 1, i.e. there's a leading 0, then I say that the conversion is a 0. So if I run down that column there, that's my binary number, right? 1110101. So it's a very sort of simple-minded way of converting from decimal to binary. So let's say you believe that that's correct. Then what we want to do is we want to shift the binary point to the left. So just as you do in, like you're doing engineering notation, right? I'm going to shift the binary point to the left, and then I'm going to multiply that by 2 to the 1 to keep the value the same. So therefore we can say that in this case the exponent is equal to 1 and the fraction is equal to this. I peel off the leading 1 because it's implicit, and I have 10101 and then a whole bunch of zeros off. So this is how this number would be represented inside the computer in double precision format. Now, here's the number 0.1 to the base 10, and we actually see that in binary it's a recurring number, right? It's not anything nice and round. There's no finite representation of it. It's got this recurring 0011 pattern all the way out to infinity. So really, this number can't be represented precisely in binary in a digital computer. And here's a particular example. There's a number 90. This is in MATLAB 90.1. I asked MATLAB to display it in all its gory detail, and we see that it's not quite equal to 90.1. It's different in the 17th digit, which is not bad. And we said before that the precision is only 16 to 17 digits. So that's what you get. Now, there's a bunch of other floating point formats. So that's 64-bit format. There's an extended format, which is an 80-bit format. And there's an uber extended format, which is 128-bit numbers. So these are absolutely massive. And the 128-bit one has got a huge range of exponents and a huge precision. It's probably used for some sorts of cosmological calculations or something like that. But at the other end, there's also some smaller ones. So there's a 32-bit representation, often called a float. It's called a float in C and Java, and in MATLAB it's called a single. And you can even squeeze a tiny sort of floating point representation into just 16 bits. But you don't have very many bits for the exponent, so the dynamic range is small. You don't have very many bits for the fraction, so the accuracy is not very good. But if you were short of space or you had a very weak computer, it might suit you. Approximately three decimal digits of precision. It's not very good. So I found this cute thing on the web. Actually, this one. Yeah, MATLAB Central, a bit of shareware called bitgui. So you just put in a binary number, so probably put in a decimal number, and it tells you what the bit pattern is. How good is that? Red for exponent, green for the fraction, and the sign bit. So there you go. So that's floating point format. Reasonably complex, and kind of hard work for a little microcontroller to do. But a big computer, a big processor can eat this stuff up very, very easily. So the x86 architecture for the longest time has had special purpose instructions that do floating point arithmetic, right? So these things have got 8 special floating point registers. They're 80 bits wide. They also can work as a stack, or you can use them as address them directly. And there are special purpose instructions there. So like load a floating point number, load a double number into a register, multiply 2 doubles, do division, do sine, do cosine, do division, do square root. These are all instructions in the x86 architecture, and it does these things very, very quickly. I'll talk about that in a moment. So x86, PowerPC, ARMS, some of the high-end digital signal processing chips all can do this IEEE 754 floating point arithmetic. There's the other format, the so-called single precision format. It keeps everything in the 32-bit number. If you wanted to do floating point arithmetic, single precision, on something like your Atmega processor, it's going to take you a lot of cycles, right? It's going to take you nearly 200 microseconds to multiply two floating point numbers together on a little microcontroller. So this is why typically people don't do floating point arithmetic on little microcontrollers. But they can do it. You're just going to pay for it in terms of speed. You have all the advantages then of a large dynamic range. You don't have to worry about numbers overflowing, about saturation, or any of those things. So it's a bit of a trade-off. So on the trade-off thing, these are sort of the two ends of the spectrum that I used, I think, in the very first lecture. You've got your Atmega 128, tiny little thing, costs 20 cents. And then you've got your Core i7 processor, like I got in here, which costs maybe $300. And you look at the difference there in power consumption, you look at the difference in clock rate, and you look at the difference in time it takes to multiply two double precision numbers together. It's many, many orders of magnitude faster. It's also many, many orders of magnitude more expensive in dollars and more expensive in watts. Yep. So this is your trade-off. So any questions about these computational issues? These are all things just to sort of store away in the back of your head to be aware of. Depends what you do in your career. Some of you may end up being bitten by such things. And just remember that these issues are there, and go and search out solutions for how to deal with them. Really all I'm trying to do here is to sensitize you to these issues and what the trade-offs are. All right. So the second of the three issues that I wanted to cover is to revisit sampling. We talked a bit about sampling in the last lecture, and I want to just reiterate that a little bit. And there was this diagram that I showed where we have two sine waves of quite different frequencies, but if I sample them at 100 hertz, they look to be exactly the same. Wherever the sampling happens, wherever those black dots are, those two waves, different in frequency, have got exactly the same value. So this is the problem we refer to as aliasing, where a high frequency can look just like a low frequency after it's been sampled. This is a fundamental artifact of having a sampler in the system. A digital system has to have a sampler. We have to go from a continuous signal to a discrete signal. We have to have a sampler, and a sampler is going to do annoying things like this. So these two smart gentlemen proposed the so-called sampling theorem, the Nyquist-Shannon sampling theorem, which says basically that the highest frequency in your input must be less than half the sampling frequency. So if I'm sampling at 100 hertz, in the input there can be no frequency above 50 hertz. If there are frequencies above 50 hertz, they'll come back, but they'll look like a different frequency. If there was 51 hertz there, it would come back and look like 1 hertz. Yeah? So a very high frequency come back and look like something low, and that would be confusing. And I'll go back to this little animation again. This is one of the issues this is the reason for this band in the S-plane. The vertical axis represents frequency in the S-plane, yeah? And we have that points, that point there might map to that point there in the Z-plane, but so does this frequency and that frequency and that frequency and so on. An infinite number of frequencies map to a single point in the Z-plane. All right, that causes aliasing. Now, there's lots of places that aliasing happens. You've probably seen on TV this effect where wheels of cars appear to go backwards, where helicopter blades appear to go backwards. Yeah? Anyone seen that? It's called the wagon wheel effect. Apparently famous in old movies. It's aliasing. It's exactly aliasing. So here's a little example. We've got the world. The world's a continuous system. Everything's moving in a continuous way. But I'm sampling it. The sampler is the shutter in the camera. which is typically opening and closing at 25 hertz. So here we see the wheel of the car, and you see that sometimes it appears to go backwards, sometimes it appears to stop, right? This is aliasing. So there's a frequency in the world, it's a rotational frequency in this case of the wheel, and because of sampling we see aliasing. So here the Nyquist frequency is 12.5 hertz, half the shutter rate of the camera, which is typically 25 hertz. That corresponds to 750 RPM. So I worked out 750 RPM, 90 kilometers an hour, 630 millimeter diameter tires, should give me the aliasing. But it's more complex than that because the wheel's actually got a number of spokes, right? So the wheel, it doesn't have to go through a whole revolution to look the same. As long as it's just moved by one spoke, it will look the same. So actually the Nyquist frequency comes down, yeah? So you'll get aliasing at some fraction of 90 kilometers an hour. So aliasing isn't just some kooky thing that happens in control systems. It can happen in lots of places, particularly with moving objects in the world. Now, so this example here, I created a 1 hertz signal and I sprinkled a little bit of 50 hertz noise on it. Any idea where 50 hertz noise might come from? Why I picked it? Yeah. There's an awful lot of electromagnetic radiation, 50 hertz, that comes from wires and lights and whatever. And then I sampled it at 28 hertz. And look what's happened. It doesn't look anything like the dominant 1 hertz signal that I would expect to see. So what's happening is we've got some aliasing components here. So as well as the 1 hertz, some of this high frequency stuff has come back reflected as a lower frequency. So I think I worked this out. I think there's a 6 hertz component in here and an 8 hertz component and some others. So these high frequencies have been aliased back to low frequencies. When added to the fundamental, it's created a signal that looks distinctly not sinusoidal. So this is where aliasing can bite you big time when you design a control system. All I've got is a little bit of 50 hertz noise from the lights. I digitize it, and suddenly my signal's not looking very good. If that was my reference, and I'm trying to track that, I'm going to end up tracking this really jagged, lumpy waveform instead of the sine wave that I'm expecting to track. So it's a big deal. So we get around this by introducing something called an anti-aliasing filter. We put in a simple filter, and we put it there in the diagram. We put it before we sample, yep? Because we want to eliminate frequencies above the Nyquist frequency before we sample, because it's the sampler that is causing this aliasing problem. So we want to get rid of those frequencies, don't let them into the sampler. So if I do that, I introduce just a very simple first order filter. In this case, I set the filter pole to 20 rads per second and repeated the experiment, and this is now what I have in my sampled waveform. So a simple first order filter has dramatically cleaned up my signal. It looks like I would expect it to look now, yeah? So that's a pretty good win. But I've introduced a filter now into my system. So if I just go back here, so I've introduced another bit of dynamics into my system. So I have the plant, G of S, and I introduced the zero order hold, and that changes the dynamics a little bit, right? We had to put a Padé approximation in there. And now I've introduced another first order pole in here, right? So it's getting a little bit complicated. I keep adding things to the dynamics, and I have to roll all them up into one dynamic model and then design my compensator for that. But if you don't do it, bad things will happen. So you do need to do the pre-filtering. So if this is the Bodie plot for that filter, which had a breakpoint at 3.2 hertz. So that's magnitude and phase, and that's where the filter pole is at 3.2 hertz. And that's where my 1 hertz signal is, and that's where my noise is. My noise was at 50 hertz. So we see that the roll-off on this filter is not very much actually at 50 hertz. It's only pushed it down about 5 dB. But certainly it's been sufficient to make a really dramatic improvement in the performance of the sampler. So this first order filter will do it for you. Now, it's important when you design the filter that the phase change that it introduces where the dominant dynamics of your plant are not too extreme. So this filter bends the phase quite a lot. It's 45 degrees of phase shift at 3 hertz. But down at 1 hertz, which is where our signal is, the phase shift isn't too much. It's maybe only 10, 15 degrees or something like that. So it's a bit of a trade-off when you design this filter, that you want to introduce a filter that attenuates the noise but doesn't mess too much with the phase of your system. So here are some rules of thumb. You want to find a good reduction in the noise level at the sampling frequency. Good is kind of a bit of a vague concept here, but here we saw that 5 dB of suppression made quite a difference. Typically, you design the filter breakpoint to be 6 to 10 times the system bandwidth to minimize the effect of the phase of the filter messing with the dynamics of your plant. And you can typically get away with a first order filter. So a simple resistor and capacitor at the input to your analog to digital converter will do the trick. It's not very complicated, but it's really important that you do it. There's an alternative rule of thumb, and that is that if the breakpoint of your filter has to be quite close to the dominant dynamics of your plant. Perhaps the noise is quite close to the frequency at which your plant's working, so you want to then use a higher order filter. Maybe you want to use a second order or a fourth order filter to roll the noise off much more quickly. That's going to have a lot more phase problem on the plant. In that case, then you've got to bite the bullet and say, okay, I'm going to consider the filter as part of the plant. The first set of rules of thumb let you get away with not changing the plant, but if those constraints don't apply, then you have to roll the filter into the dynamics of the plant. So ideally go with the first set of rules of thumb. This is what you need to get away with it. If you can't do that, things are a bit more difficult, the noise is too close to where you want to operate, then that's what you've got to do instead. So a question that people often ask is, okay, we've got all this, we've been talking a lot about the problems of sampling slowly, we've got this aliasing problem. What if I just sampled really, really quickly? Yeah? Then I'm not going to have any of this aliasing nonsense. I've only got the problem with 50 hertz because I'm sampling, at 28 hertz. What if I sampled at 10 kilohertz? Yeah? Then all this aliasing problem maybe is going to go away. There's a couple of reasons why you don't do that. Well, the first is that the Nyquist limit still applies. So even if you sample at 10 kilohertz, noise at 11 kilohertz is going to come back and bite you. So you're still going to need an anti-aliasing filter to get rid of all the noise any noise above 5 kilohertz is going to come back and bite you. Yeah? So you still need an anti-aliasing filter. So you haven't won there. The other one is computation time. So if I make my control system run at 10 kilohertz instead of, say, 20 hertz, I'm having to do an awful lot more computation. I'm going to have to bite the bullet and go up to a more powerful microcontroller. Yep. And maybe there are economic reasons why it doesn't make sense to do that. So certainly computation time is an issue. We need to consider computer power and cost. But the other thing that really stops you doing this is signal quantization. Does anyone know what quantization is? Yeah? Who doesn't know? Some people don't know what quantization is? Okay. I'm trying to stagger over to the whiteboard. Oftentimes when you take a signal from a continuous signal and you read it into a computer through an analog to digital converter, so say the signal goes between, say, plus 1 volt and minus 1 volt, yeah? We read that into the computer through, say, a 10-bit analog to digital converter. So 1 volt becomes 10-bit converter, that would become 511, and this bottom one would become minus 512. Right? So we're assigning continuous things to numbers, to integer numbers. So what's going to happen is that there's going to be, in fact, a small range of voltages that are going to get mapped into the number 511. It's going to be a small range of voltages which are going to be mapped into the number 510. Because basically we've got 1,024 numbers have got a map to a span of 2 volts. So that means that we have basically 2 over 1,024, 1 on 512. Every 512th of a volt that we go up, we go into a new number. So a continuous waveform comes in, and what comes out in an exaggerated fashion is something that's a bit steppy. and it should be in phase with that, yeah? So it becomes like a staircase instead of a continuous signal. So that's quantization. It's quantization in amplitude, in value, not quantization in time, which is what I've been banging on about most of the semester. This is quantization in a different dimension. But they interact in a really bad way, which is what I'm going to show you in a moment. So signal quantization is important. So let's say I have a cosine wave at the top, continuous time cosine wave, and I want to compute its derivative, right? So I compute its derivative using that transfer function there, and I get the sampled sine wave at the bottom. So everyone can see what I've done there? Continuous time signal, I've sampled it, I've applied this transfer function which is equal to a derivative function, and there at the bottom is a sine wave, the derivative. So I sampled the 1 Hertz sine wave at 20 Hertz, compute the derivative. All looks lovely. And now I can sample it at 100 Hertz, and I can compute the derivative, and it looks lovely. Well, the samples are much more closely spaced together, right? So all those little circles have all laid on top of each other and given that really thick line. And there you go. But if I quantize my signal first into just 100 levels, what's going to come out is a signal that looks like this. And it's going to look, it looks like rubbish, all right? So instead of the nice sine wave, what I've got is this thing that looks like a ziggurat or a pyramid or something like that. It's because I quantized the signal into 100 different levels. If we zoom in on it, we can sort of see what's going on. I've zoomed in on one of the flat bits at the bottom of the input wave. And you can see that the quantization has made it flat for quite a long time. So if I compute the derivative across the flat bit, of course it's going to be 0. Right? For quite a long time, the output is 0. Right? And then it kicks up a notch, and it has got a particular value for a little while, and so on. So it's the quantization is causing this bad effect. And we can think about that the input signal is quantized. So we can represent the value of our signal y as n times some little increment, some little delta. So if that's this little step size here, if I call that delta y, then my signal is an integer number of those that smallest increment that can possibly be. N is an integer in this case, yeah? So if that's the case, then the velocity, which is delta y over delta t, you can show is going to be m, another integer, times that thing. And that's the velocity quanta. So the minimum size velocity step that I can estimate is a function of the quantization level of the input signal divided by the time interval. So if I make the time interval smaller, I'm saying that the increments of velocity get bigger. So I can estimate the velocity as either 1 meter per second or 2 meters per second or 3 meters per second. If I double the sample interval, then I can only say the velocity is 0 or 2 or 4 or 6 or 8 meters per second. So this is a case where reducing the sample time makes implementing something like this very difficult. So here's another example where I have doubled the sampling rate again, and we can see the signal is incredibly quantized now. There's really only 1, 2, 3, 4, 5 possible values for the velocity. And if I double the sampling interval again, there'd be probably only 2 possible values of velocity coming out. And the signal is now really noisy, right? It's this horrible ragged step thing with all this kind of grass on it. So if I was to compute a PID controller, I'm going to take this derivative, multiply it by a gain, right, and feed it back into my process. Process is going to hate this, right? This noise is going to make the controller sound horrible. If it was a motor or something like that, you'd hear this, and you'd feel it on the motor shaft. It would be very bad. So this is a reason why you can't just crank up sample time and say it's going to get rid of all my problems. If your signal's quantized, then almost everything we deal with is quantized, right? The signals we measure come in through an A to D converter, they come in through an incremental encoder on a shaft, they're all quantized. Quantization in time interacts very badly with quantization in value, right? So this is getting to be a really big trade-off of lots of different things. Just park all these things in the back of your head. Maybe you'll need them one day. Last little bit I want to talk about is back to control design. And to talk about the destabilizing effects of time delay. So there's probably actually many cases in your everyday life where you've been destabilized by time delay. Now perhaps you haven't thought of it in these terms, but how about this? Everyone's experienced this, right? Two people talking with a time delay in between them, right? So you go to talk, the other person goes to talk, you both think, oh, we're talking, our control system says we should stop, and then there's a long gap, and then you both start again, right? So on a normal landline where it's not going through Skype or not going over satellite, we can have phone conversations quite well. We can have conversations very well face-to-face because there's really high bandwidth, there's no delay. But as the delay starts to rack up, it becomes harder and harder to have a conversation. Yeah? So this is an effect of, I couldn't write down the dynamic equations for this, but it is very definitely time delay that is destabilizing the controllers in each person's voice output thing. Yeah? Another example, when you learn to drive, the kangaroo hop. Yep. The car starts to go, you think, oh, I'm going too fast, you pull your foot off the accelerator, you think you're going too slow, and you push it down again. And it's basically you're reacting too slowly. So there's a delay between what's happening and you pushing the pedal of the accelerator, and that has this destabilizing effect of kangaroo hopping. That's very definitely an oscillation that's induced by delay. Now this is very well known in some other fields. In aerospace it's called pilot-induced oscillation, and it can be much more scary in an aircraft than it can be in a car. So I found this little video, which is pretty cool. So here's a fighter coming into land, and I've got no idea how old this is. He's flaring. Yep, he's oscillating. So, if you go and consult YouTube about pilot-induced oscillation, you'll find a lot, particularly the shuttle. There are lots of shuttle landings where there's evidence of pilot-induced oscillation. Scarier there because he doesn't have engines, so he's got quite limited control authority. So again, an example where the delay in the control system, which is mostly cognitive delay in the human pilot, between what's being sensed, there's a control algorithm going on in here, and then he's actuating the sticks, is causing the system to become unstable. So again, a slide from a while ago, and we talked about on the Z-plane where delay lives. So delays introduce a pole at the origin. Yeah? So that's where z equals 0. Poles there are delays. Another example from a few lectures ago, we had this simple continuous time plant. I drew the root locus. You can vaguely see the unit circle there. Two poles come together and then they go up, and they stay inside the unit circle for a while, then they leave the unit circle and go around and do the usual kind of pole thing. So I introduced a lead compensator, and by judicious choice of gain, I could move the closed loop poles to where the little squares are. So, they've got a nice damping ratio, they've got a nice natural frequency. Pretty simple bit of control design. Yep. And that's the step response. So it seems to settle in about 6 steps, 15% overshoot, all pretty nice. Now what I'm going to do is I'm just going to add an extra pole in there, right? I'm not going to change the compensator at all, same dynamics, I'm just going to add an extra pole at the origin. And we can see that the root locus has changed quite significantly. We've got an extra pole in there now, and it's going to want to go somewhere, so it's going to change the way the branches of the root locus move. And if we look at the step response, we can see that it is now quite seriously oscillatory. Yep. I had another pole, and yeah, it's not good. With that loop gain that I chose, the closed loop poles are right on the unit circle itself, which would indicate continuous oscillation, and that's what the step response shows. So all I did was add 2 time steps of delay, and the system's gone unstable. Adding just a single time step of delay made it certainly much more oscillatory than it used to be. So we've gone from some sort of hand-waving examples about cars hopping and aeroplanes not being flown very well through to, in terms of discrete time dynamics, what does it mean? Extra poles at the origin are unhelpful and will lead to instability. Many industrial processes have got what's called transport delay. And that's where there's a delay, a pure time delay between the actuator and the sensor. So here's a couple of examples. The top one, I've got some fluid flowing through a pipe. Could be air, could be water. And I've got a heater at one point, and I'm measuring the temperature some little distance down the pipe. So there's a delay. If I input a step into the heater through U, it's going to take a while before that warm fluid gets to my sensor. So the dynamics of the system is pure delay. Another example down the bottom is a conveyor belt. So I've got a chute which is trying to put a uniform layer of stuff on a conveyor belt. And I've got a height sensor somewhat down the track, right? So there's a delay between what I do with the chute and when I can detect what it's done. And so I need to design a controller that can keep this stable even in the presence of delay. A big example in industry is paper machine. Paper machines are big, complicated things. They basically start with this white sludge, which is like very, very dilute paper fibers, like white water, right? And that gets put onto felt, and at the end you want to measure something like the thickness of the paper. And it goes through all these rollers and all sorts of process, but your measurements are quite late, and you actuate right back on the left-hand side. So there's all sorts of delays in the heating control, in the application of the amount of liquid that's being poured onto the felt rolls. All sorts of time delays in this. Steel rolling mills would be another one where you've got great big rollers that you open and close to control the thickness of the steel going through, and then a few meters down you've then got the laser instruments that measure the thickness of the roll, and you've got to keep that stable. So this kind of pure delay process is very, very common in industry. There's also another one that you've all got in your house and probably had experience with this morning, that you may not have thought of it in that way, and that is controlling the temperature of a shower. Okay, so you turn the tap down here, and after some time, the different amount of hot water goes through all the pipe and out there and then falls on your head, and you feel it. So if you try and change this thing too quickly, you turn it up and then it's too hot, and then you turn it back and it's too cold. Everyone's been there, right? No? Oh. All right, well done you. But for everyone else, this is the thing. So you just got to change it slowly. You should just turn it a little bit and wait, and then decide whether you should turn it some more or less. If you just keep thrashing around, you get into this pilot-induced oscillation, and you probably scold yourself. So as a little exercise, have a think about this, right? Here's a shower. Water's flowing out, 9 litres a minute, the Australian standard. And say you've got a 1 metre pipe, 1 metre of pipe between the tap and the shower head, and the pipe's 13 millimetres in diameter. What's the delay between when I turn the tap and when I notice the change in temperature of the water? There's an exercise. So pencil and paper time. It might surprise you. It's not instantaneous. Anyone got an answer? Anyone got an answer?
I have 0.9 seconds.
0.9? Yeah. I got more than that, but I think I got the reciprocal of that. I'm not saying I'm right. I think you're right. 6? I think that's too much. All right, we've got a few data points in the room. That's good. So here's how I did it. So 9 litres a minute is 0.0015 cubic metres per second of water coming out of the shower. And the volume of the pipe between the tap and the shower head is 0.0013 cubic metres. So just looking at the units of this thing, I would want to divide the cubic metres. So it should be 0.00013 cubic metres over 0.00015 cubic metres per second. Yeah? So cubic metres will cancel out and the seconds goes to the top. So I think your answer up the back was correct. Yeah, so it should be approximately 0.9 seconds of delay. Good. So maybe sort of unexpected that the time between when you turn the shower tap and when it actually, the time actually falls on your head's probably a bit longer than that, because it's got to go through the shower rose and it's got to fall down through that kind of distance. So yeah, of the order of a second between when you turn the tap and when you might notice that it's changed. All right, so much for showers. The other area where the time delay can be really important is in large-scale systems, large-scale network systems that have got delay. Computer networks are really complicated things. Data goes through, to get from point A to point B, it goes through a whole communications stack. It goes through routers and gateways and whatever. The packet is being processed in every single little rectangle here. It's being pulled apart, it's being read, some calculations being done on what to do with it next as it wends its way from one point to another. So even though at the bottom level you've got gigahertz, gigabit, Ethernet cables and whatever, there's lots of computing that has to be done on every single packet to get it through. And networks have got some odd characteristics too. Generally they're sort of quite interconnected meshes, so packets can take quite different routes through a network. So packets often don't go, packets from A to B don't necessarily always go along exactly the same paths. Some will follow different paths, and the paths will change dynamically over time as congestion takes different bits of the network out. So networks are really difficult things to deal with because the delays are significant and also quite time varying. And this is what you encounter with something like Skype. The delay is all over the place and significant. The other characteristic of network links is that the sort of response curve is that as the load goes up and up and up, they go quite nicely, and then they fall off quite catastrophically. So when a network link gets overloaded, sometimes Ethernet maybe more than 30% load, then the performance just goes almost to zero. That's just a particular characteristic of networks. So bottom line, delay is really, really common in the world, and controllers need to deal with that. So here's a root locus of a very simple system that's just got pure delay. So it's a system that's got two poles at the origin, it's just pure delay. And if I compute the root locus, the two poles at the origin just go like that. Yep. So I wind the loop gain up enough, it will go unstable. But what I can do is I can design a pole placement controller for that system. I can place the poles so that I get a natural frequency of 1, a damping ratio of 0.6. So although the plant might have just a pure delay, it might be the water temperature control problem we talked about or the conveyor control problem, I can place the poles of that system so that it's got a nice second order response. Yep, so there it's got quite a nice rise time, very little overshoot. And I do that simply by designing a pole placement controller for it, and I place the poles to give me that characteristic equation. So there's nothing extraordinary or unusual, if you like, about taking something that's got pure delay, kind of very odd dynamic. In continuous time, in the S-plane, you can't represent something with pure delay. That's something that's really special to the Z-plane, where pure delay is represented by a pole at the origin. But we can make it behave like a lovely second order system if that's what we want to do. Interestingly, we can do the inverse. So let's say that I've got a system that's got second order kind of dynamics. It's got sort of poles and zeros, that sorts of places in the examples you've looked at so far. Could we put the poles at the origin so that it looks like a system that's just got pure time delay? And you can. And that sort of controller is called a deadbeat controller. And so here I took a system that we've looked at a few times, S over S plus 0.5. And so it's got a pole at S equals 1 and a pole at S equals minus 0.5. And I placed both the poles at the origin on the Z-plane. And the top graph shows the step response. And it looks like the step response for something that's just got pure time delay. It's got no overshoot. It's got infinite rise time. But it's two sample times late. Yeah? So I've turned it into a pure second order time delay. So it's got a 2 time step delay, and then it just goes up and it's flat. So that's a trick that you can pull. You can turn a system with arbitrary dynamics into the dynamics that look like pure delay. A bit of a problem with a deadbeat controller is that it requires quite a large control input. So you can see there that the control input goes up, quite high to about 1.5. And these are all kind of arbitrary units, but in real life, a deadbeat controller will typically try and request huge inputs into the plant to get it to move in this kind of way, and that's not going to happen. So, the example of a supertanker, you have a very large plant like this, and if you try and turn its dynamics into just a pure time delay of 5 seconds, you're going to need a huge amount of power in order to do that. So you need to think about that with a deadbeat controller. It's in some ways, the dynamics of the pure time delay are not very compatible with the natural dynamics of the system. And the more different you're trying to make the dynamics appear, the more you've got to push the system, the bigger the control inputs that are required. And in practice, you're not going to find very many cases where this will work. Just a little point of notice here. I use the function here. I'm designing a state feedback controller here. And previously, I've used a function called place. So place, you give it the phi and the gamma matrix and the poles, and it gives you the state feedback gain matrix. Here I've used a function called akka instead of place. Now, the function called place doesn't like to place the poles at the same location. So it won't let me place 2 poles at the same place. There's some complications around that, but certainly for these second-order systems, I can't place 2 poles at exactly the same location using the place function. The algorithm doesn't allow it. The akka function does allow it. So in some ways, they're kind of equivalent. For low-order systems, place and akka give exactly the same results. For 10th order systems and above, place is much better than akka. But for low order systems, makes no difference. And akka allows you to have what's called pole multiplicity. I can place 2 poles at the origin. Right? There's my supertanker. And that's kind of it, really. I don't really have sort of too much more that I want to add, so I'm just going to kind of reiterate some of the points that I'd like you to take away from this control unit. The control design process you've met a number of times, I'm hoping, in your education. And these steps are really invariant, right? The first thing is to obtain a model of the plant. And there's lots of ways of obtaining models. We haven't really talked about that. It's mostly assuming that you can figure it out from looking at things like data sheets of motors and things like that. But the first thing is to start off with a model of your plant. Next thing is to say, what does a good control look like? What's your performance criteria? And so you've met all sorts of measures like rise time and overshoot and whatever, damping ratio. So you need to decide what it is that you're wanting to get out of your control system when it's working well. And then there's a whole range of ways of designing compensators in continuous time, in discrete time, in transfer function form, in state space form. Right? There's no one right way. It depends a bit on the complexity of the system, depends a bit on also what you know best. But you design a compensator. Next thing then is to simulate the compensator in the plant in something like Simulink or MATLAB and test that it's working well. You're making a lot of assumptions at this point, right? You're making an assumption that the model of the plant that you have in your simulation is a good model of the real plant. But it's a good way to sanity check it. It's a good way to see, is it doing the right thing? Is the performance what I expect? You can do things like vary the sample rate, see whether it makes things better or worse. Change the closed loop poles around. Look at what's the input to the plant. Is the input to the plant just too excessive? Am I trying to push the plant too hard? Do I need to perhaps back off on that a bit? So you can adjust the closed loop poles. In the LQR controller, you'd probably adjust the Q and the R matrices to try and do these same things. Lots of ways to skin this particular cat. Next step then is to implement the compensator. You write some code, you put it on a computer. Desktop computer, could be an embedded microcontroller. You've got to think about the language, about the timing issues, about quantization issues, about dynamic range issues, and all of those sorts of things. And then you take the big breath and you turn your controller on and see how well it performs. Does it perform like you expected it to? If it does, it's great. End of story. If it doesn't, then you go back and think, well, okay, what's different? Did I code it wrong? Is my model wrong? Is there something about the plant that I don't quite understand? So these are all important parts of it. And typically it's iterative, right? You get to the bottom and it's not quite what you'd like, so you go back and you do it all again and again and again until you've got it right. But certainly for a very large plant, the step 6, when you actually turn the controller on for the first time, it's kind of can be a bit of a leap of faith. I had some stupidities in my time. One was with a very large machine with a drag line. I think it had 2,000 horsepower of motors, and I got a sign wrong in my controller. So it was a positive feedback controller instead of negative feedback controller. That was interesting. So I guess initially you got to have your hand near the big red stop button and always do things safely. When it comes to creating the model of the plant, there are actually a number of aspects, and it's more than just the plant itself, and we've touched on some of these things today. So the open loop dynamics of your system, the dynamics of the plant, absolutely, and very importantly, and probably dominantly. But the zero order hold, which we always have in a digital control system, you may need to account for its dynamics, right? Using the Padé approximation or the Z transform. If you put an anti-aliasing filter in, you might need to make that part of the dynamics of your plant as well. If you've got any delays in your system, perhaps due to network sensors or due to computation time in your lame little microcontroller, then you need to account for that in the system dynamics. So your system dynamics consist of all of these things. Roll them all up into one discrete time model, design your compensator, and away you go. Sometimes you can get away with leaving these things out, and sometimes you can't. Right? So maybe it's always good to try and be precise and squeaky clean and take account of those things. Last thing, second last thing. Some ideas I'd like you to take away from this is that in digital control, we're dealing with sequences of numbers. We're not dealing with signals, right? So it's a sequence of numbers, a list of numbers that occur at fixed intervals in time. The Z transform, in many, many respects, is just like the Laplace transform. So Z is really like S. It lets you do a lot of the same things. There's a mapping, unique mapping from one to the other. There's a non-unique mapping back the other way because of aliasing. There's lots of ways we've learned about discretizing a transfer function or a state space system, right? We've covered lots of ways of doing discretization. They're all equally valid, and the next slide is some rules of thumb about when they're appropriate. And we can design a digital compensator for a transfer function form or for a state space form. Doesn't make any difference, right? It's just whatever's convenient. If the system's only got one input and one output, you might as well treat it as a transfer function. You can do it in state space, but it doesn't buy you anything. If it's got more than one input or more than one output, or both, then it's much more convenient to consider it as a state space system. Yeah, a simple one input, one output, do as a transfer function. It would be easier. Digital systems always include a sampler, and samplers always lead to aliasing. Yeah, so anti-aliasing filters are going to be your friend. Zero order hold, you're always going to have a zero order hold. It might be explicit in a D to A converter, or it might be implicit in setting the registers in a PWM motor driver. Yeah. You always have a zero order hold, and it introduces a delay. You need to account for that. Computation issues. Computation takes finite amount of time, and depending how big that time is, it may or may not impact the dynamics of your plant. You'll have numerical issues about the range of the numbers, about overflow and so on. And you'll have quantization, which we showed has interesting interactions with the discrete time nature of systems. So this line I think I put up in the last lecture or the one before. These are the sort of rules of thumb for discretizing. They're all in a place in the lecture notes, so you can perhaps get to them more easily. If your sample rate is really high, then you can just use the simple Euler method for discretizing. If it's kind of middling, you probably should, what am I saying there? you should include something like the Padé approximation to the zero order hold. If your sample rate's really quite low compared to the system bandwidth, then you really should use the zero order hold and the Z transform to discretize your system. You can use the Tustin transform in that sort of middle bracket. It will work well there. But all of these things is really a little bit of trial and error and a bit of experience. So that's all I have to say about control. It's an interesting field. There's a lot more to cover, but I think this is, if you go into the world with this, I think you'll be well served. So we're done and shoot in half an hour. Thanks, guys.